Predicting motion, a falling object. In this presentation, I will show a falling object and use Python to predict the object's final velocity and final position using Newton's second law. I will also show the effect of drag on the object and how that affects the predicted final position using a computational model. I will also discuss some potential what-ifs as well as errors. So first I will show you the video using Tracker. Here's the video. As you can see, the position points are plotted in this chart below. So some initial data. The initial position of the object was 0.011 meters in the y direction. The initial velocity was negative 0.835 meters per second, and this was calculated using the first two data points in our table. The mass of the object was 0.022 kilograms. So Newton's second law, we'll be using the equation the final velocity equals the initial velocity plus the F net divided by mass times delta t, as well as the final position equals the initial position plus V average times delta t. Now in this case, F net is not equal to 0 because you have a force called the weight force acting on the object. The weight force is calculated by the negative mass times gravity. So we're now going to put that into Python code. W is equal to the negative mass times gravity, and W is then set to F net. F net is then put into Newton's second law. So using that, we produce a computational model that shows the weight force acting on the object. Now data is produced, and showing in this data, it shows that the observed and the predicted position match up at first, but then tend to deviate. So this shows that there's another force acting on the object, and this force is called the drag force. So now we have to include the drag force into the F net. Drag force is calculated by B times velocity, and in this case B equals 0.01. So our new F net is now weight force plus drag force. So we now put that into our Python code, which is shown here. The weight force is still the same, and the drag force is calculated here. So we set F net equal to weight plus drag force. Our Newton's second law equations still stay the same. The only thing that's changing is our F net. So now the data is produced, and as you can see, the blue line, which shows the position with drag, coincides a lot better than the red line, which shows the position without drag, proving that there's another force acting on the object called drag force. So here's a computational model with drag force. With or without drag force. Including drag force into the Python code makes the data more accurate because you're accounting for the area surrounding the object. Without drag force, your prediction for your new position is very inaccurate. Only the model with drag force shows terminal velocity. Terminal velocity is where your weight force equals your drag force, producing a constant velocity. After the object is initially dropped, the drag force and weight force are equal, causing the velocity to eventually become constant. What if? What if the ball was not dropped from rest? The terminal velocity would be different than if the ball was dropped from rest. The terminal velocity would occur at a different time than the terminal velocity of a ball being dropped from rest. It will take less time for the object in motion to reach terminal velocity because the speed is greater, so the magnitude of the drag force is greater. Some potential errors include not enough data points due to the frame of the camera, as well as for my drag force equation, my B may have not been accurate because I calculated the B using trial and error. Conclusion. The computational model that uses the combination of the weight force and the drag force is more accurate than the model that just uses weight force as the only force acting on the object.